So our third flux is going to be the Engquist-Osher flux, and we're seeing that we got a bit of an increase in complexity here. We have a numerical flux defined as some integral of, well, a min or a max of the derivative of the flux function integrated on the variable itself, phi itself. So again, that's why I'm trying to work this out for the simplest case, so we can get a bit of a feel for how we would go about computing something like this. Just so that you sort of understand why we're increasing this kind of complexity. This has to do with certain properties beyond conservativity and consistency that we want our numerical fluxes to have. The property that I'm talking about here is that it's monotonicity. And that means that we want to have this flux function to be decreasing with respect to both of the arguments, phi plus and phi minus. And that has positive properties in terms of the resulting oscillations that you would get if you would perform a DG simulation on a more complex model problem than the advection diffusion model problem. So I suppose one of my objectives here is just to give you a bit of a feeling for what range of options we have, and that we have options of multiple levels of difficulty, and that different choices lead to different schemes with different properties, and depending on the problem that we're dealing with, we might want to pick one over the other, right? So I'm giving you a bit of an overview, I guess is my objective here. But for the example of the linear advection diffusion problem, we see again that our Engquist-Osher scheme is actually going to simplify quite a lot. Well, what do we get? We have f of 0. Well, f of 0 is simply going to be equal to 0. So then we have the integral from 0 to phi minus of the minimal of the derivative of phi, derivative of f with respect to phi, so that's going to be equal to our advective vector, dotted with n plus or 0, integrated from 0 to phi, so integrated over phi. Well, what is a dot n? A dot n is going to be a positive value, right? We're considering again our element and advective orientation as drawn here on the right. So a dot n is going to be positive. So the minimum of a positive value in 0, well, that's going to be equal to 0. So this whole integral drops out. Then we have the second case, 0 to phi plus of the maximum of, well, the same thing, a dot n plus n 0. So now we have the maximum of a positive value and 0. Well, that's going to be that positive value. So this is simply going to be a dot n plus. So then I have the integral from 0 to phi plus of a dot n plus d phi. Well, that's going to be equal to a dot n plus times phi plus. So, and performing the same trick as we've done 3 times before now, we get phi plus phi minus dotted with n minus, well, that's simply going to be the opposite of that, or a dot n minus phi plus. So again, we see that we get the R-point flux. Now, to perfectly make that claim, I also have to consider the case where we're flipping our elements or we're flipping our advective direction. So then we would have minus and plus with a. So then our first term would be non-zero and our second term would be 0. So then you would end up with, well, integral from 0 to phi minus of a dot n minus, or sorry, I should still say n plus. That being this vector now rather than this vector. Oh, couldn't see that second. Rather than the vector up top here. D phi. And the second integral from 0 to phi plus is going to be the maximum of, well, a negative value, right? A max of a dot n plus is going to be a negative value, or 0. Well, that's going to be equal to 0. So that second integral drops out. So we only have the first integral left. The minimum of, maybe I should be a little bit more careful here. Let me write this out. So we have the minimum of a dot n plus or 0. Well, this is going to be a value, a negative value. So the minimum is actually going to be equal to, well, that guy times the phi. Well, that's going to be equal to the integral from 0 to phi minus of a dot n plus d phi, and that's going to be equal to a dot n plus phi minus. And if we then evaluate f Engquist-Osher dotted with n minus, well, that's going to be equal to a dot n minus phi minus. Yeah, so again, we see that in both cases, whether we have the element set up at the top here, we get the upwind value. And for the element configuration here at the bottom, we also get the upwind value. So in all cases, the Engquist-Osher for the linear advective scheme is again our upwind linear flux. So I think I'll, in this video, I'll also consider our last flux, just to keep things a little bit compact. That's going to be a pretty simple one, actually. That's going to be the rho flux, but also a very popular one, due to its simplicity. That's trying to fix a little bit of the issue of the Lax-Friedrichs flux that was to this overly diffusive property. And it is defined as a switch between three cases. That is a case of f of phi plus dot n plus, a case f of phi minus dot n plus, and a case of where it's simply equal to the Lax-Friedrichs flux. Yeah, so this is a fix on top of the Lax-Friedrichs flux, trying to mitigate part of its overly diffusive behavior. So pretty much the last cases where this overly diffusive behavior does not occur, then we get back to the Lax-Friedrichs flux. But we picked the first one if the derivative of our flux function with respect to phi dot n plus is positive. We picked the second one if that derivative is negative. And we pick this guy if we have any other case. And now you think, how is it possible that we have any other case? Because, well, we're evaluating these for all choices of phi between phi plus and phi minus. So for all phi between phi plus and phi minus. So what is that going to be in the linear advective case? Well, we know that the Lax-Friedrichs flux is going to be the upwind flux. And I'm not going to work this out because you can actually already see this quite straightforwardly. If our elements are such that n plus dot a, remember this was simply a in the linear advective case. If n plus dot a is going to be larger than 0, well, for all phi, well, because we're dealing with the linear flux, we don't even have to look at all choices for phi. Our derivative of our flux function with respect to phi is going to be independent of phi. So in fact, we'll only have to consider these two cases. So if a dot n plus is larger than 0, well, that means that the plus element is the upwind element. And indeed, we get the flux evaluated at the upwind element. And if it is smaller than 0, then that means that the plus element was the downwind element. And then we choose the opposite one, which is the upwind case. Okay, so that was the last flux, and again, this falls back to our upwind flux in the case of the linear advection problem. So then there's still a handful more, Lux-Vendroff, Van Leer, HLLC. So there's really quite an extensive bookwork of fluxes to choose from. My objective here is not to give you a complete overview of all possible choices. I want to give you a taste of what's out there, and a feeling for partly the complexity in our choices here, but also the freedom in our choices here. So that we really do have a whole bunch of different options, and the different options are going to give us different methods with different characteristics. Some notes that I want to go through, though, some points that I still want to emphasize are that all these fluxes, they do not originate, or they were not originally designed from the idea of coming from a discontinuous Galerkin method. These are all fluxes that have been developed for decades in the finite volume community, and then when they started developing discontinuous Galerkin methods for hyperbolic problems, well, they ran into this issue that they have to evaluate a flux on an interface where it's not clear where you want to evaluate the flux precisely, on the one side, on the other side, or in between. And then they realized, well, that's exactly the same issue that we have with finite volume methods, and people have been trying to solve that for a long time. So then they tried to use all these fluxes also for discontinuous Galerkin methods with success. Right, so the point here being that these fluxes actually originate from finite volume methods. That being said, certain characteristics that are true for the finite volume part of things do not hold for the discontinuous Galerkin side of things. And again, the example being that the Lux-Friedrichs flux is not necessarily limited to lower order convergence for the G method. Now, I think I've said this a couple of times, but they're not all going to be the same for nonlinear problems, right? So the Burke's equation being one example, you would get different expressions for the different fluxes, and the fact that we had the upwind flux all the time for our linear advection diffusion or linear advection case is just a particular choice. Yeah, but I think that's an important example because it gives you a feeling for the connection between physics and math for all these fluxes, right? For the simple case, and when we have pure transport of some chemical forward, then we get this upwind behavior, which is what we expect physically. So I try to write everything to be independent of the dimensionality of the problem, 1D, 2D, or 3D, by using these vector products. Often it's not quite so clean, and I'm not 100% sure that I did this consistently everywhere, because many of these in literature are only cited for the 1D example, where you simply you don't have a plus or a minus element, you just have a left and right element, and the left element always has a plus normal vector. So that was my attempt at generalizing this a little bit. I hope that worked out. What is important though is that for the multi-D cases, we might actually have, and also actually for the 1D case, we might have conservation laws that, no, only for the multi-D case, sorry. Conservation laws that are not scalar conservation laws, like the one that we're considering right here, where we have a scalar phi, which may be a concentration that is conserved. But you might have vector conservation laws. You might have conservation of momentum in all directions. And then sometimes it's a little difficult to write that into a set of scalar conservation laws. I'm not even sure if that's always possible. Suppose it's not, then it's important to realize that the flux function actually becomes not a vector, right? Right now our flux functions are vectors, a dot phi, or a times phi, that's a vector. But if we have not a scalar conservation, but a vector conservation law, then our fluxes become tensors. You know, we get a tensor-valued flux. So how do these things extend to that case? Well, you would actually have to, because sometimes we're dealing with certain maxima and minima, right? And how do you determine a maximum or a minimum of a tensor or a vector? well, you would have to work with eigenvalues. So things become even more complex in those cases. Then one thing that I mentioned, I think, in a previous video, is that all these fluxes are designed in such a way that they are monotone, decreasing functions of both arguments. That has to do with suppressing certain oscillations. And lastly, you would often find in finite volume and also in discontinuous Galerkin literature that they're referring to these numerical fluxes as approximate Riemann solvers. And the reason for that is that they originate from trying to analytically solve a step function problem. So a function where you would have in 1D, a 1D step function problem, where this is your initial condition. And then you can work this out for our hyperbolic conservation law. So suppose this is phi, so then phi t of plus the divergence of f of phi. So this is called a Riemann problem. And there is certain behavior to this problem. You have different types of shock waves. And each one of these fluxes is a certain approximation to how that would behave analytically. And that's what they're trying to capture. And again, that also comes down back to that monotonicity of these flux functions. That comes back to the origin of these flux functions as approximate Riemann solvers being approximations to trying to solve this extreme case. And you can also understand this precisely the case that we're trying to solve, because for a discontinuous Galerkin method, even though we might have a smooth true solution, our DG method might actually have a discontinuity. That's why these are so relevant for DG methods. Okay, I think that's the list of points that I had and that I wanted to address before kind of closing this chapter. Maybe in the next video, maybe next on Thursday, I'll show some experiments, some numerical experiments, just to give you a feeling for what these numerical solutions may look like for potentially more complex cases. And then we will actually move away from purely hyperbolic equations. This is a hyperbolic equation, hyperbolic conservation equation, because we will realize that actually diffusion is very important also from the physical perspective. The hyperbolic conservation example is a limit for the advection diffusion case where the diffusion is equal to 0. But in many cases we are interested in diffusion. So we somehow also need to be able to treat diffusion problems with DG. So that's the last thing that we'll talk about. So how do we go about doing that? And then that's the end of the section on discontinuous Galerkin methods. Okay, thank you for your attention, and see you next time.